Hello everyone. On this video we will be going over double integrals for non-rectangular regions. Alright, so first thing we are going to do is look at our 3D graph here. So let's say in our three-dimensional plane we have our x, our y, and our z. Okay, so let's say if we had a shape that looked kind of like this. It was straight on that end. And straight there. Okay, so it's non-rectangular. It's not a rectangle. Some odd looking shape. Okay, so let's say right at this end of the shape, this is some value A. And this is some value B. Okay, now if we wrote this, just kind of getting rid of the three-dimensional plane and just looked at the XY plane, that shape would look kind of like this. Alright, that's your X and that's your Y. Okay, so here this is our X is equal to some value A and X is equal to some value B. Okay, now if we wanted to find the area of this particular shape, we have to figure out the Y boundaries. Okay, so in this case, our Y would be some function of X, and this Y would equal some function of X. Okay, so for these two portions of the graph. Alright. Okay, so this gives us our type 1 region that we will call it. Okay, so what if our region is bounded on the left and right by A and B? So if the region is bounded on the left and right by the vertical line x equals A and x equals B, which is what we have here, and below and above by two functions of x. Okay, so and above and bounded above, that's a key word there. I think it's probably a necessary word, and bounded above and below by continuous curves, meaning there are no openings, no anything that will make it non-continuous. By continuous curves y number 1, let's say y is equal to g number 1 of x. So our first function of x, and y is equal to our second function of x. Where we can say that our first function of x is smaller than our second function of x. So in this case, our first function of x is less than or equal to our second function of x for the x interval between A and B. Okay, now if this is the case, your double integral over the region of our function of f, well, function of x and y with respect to the area of the region is equal to the integral from a to b and the integral from your first function of x to your second function of x, f of x, y with respect to y with respect to x. Okay, now you notice here, since it's with respect to y, of course, your two functions that are equal to y would be on the inside. Okay, so you want to make sure you don't mix those two up. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and go to our next page. Okay, so let's say this time on our three-dimensional plane, we have our x, our y, and our z. Okay, so let's say this time you have a function that looks kind of like that, where this value is c and this value is some y equals some number d. Okay, so once again, if we move this and just focus on the region, not focus on anything above it. So we're just focused on that region. Then this function would look kind of like this. Where you have your horizontal lines, y equals c and y equals d. Okay, now in this case, to find the area between there, you would have to have your functions between some x value on this side and this side. So on the left, we'll let that x value equal some function of y. That should be the first function of y, and this one will equal our second function of y, to represent the left and the right that are no longer straight lines in a rectangle. Okay, they can have any odd shape. The only straight lines we have are right on the ends here for our y values. Okay, which brings us to what we'll call our type 2 region. Okay, so if the region is bounded above and below by horizontal lines, so if the region is bounded above and below by the horizontal lines, y equals c and y equals d. Okay, so we also know they're also bounded on the left and right by, they're not lines, but they still are functions. Okay, and bounded on the left and right by continuous curves Okay, we'll say x is equal to our first continuous, oh, that should be y, our first continuous function. And the x on the right is equal to our second continuous function. Okay, where we know our first function is smaller than our second function. Less than or equal to our second function for the entire section between C and D. So C between C and D. Okay, so if that's the case, then the double integral formula we're going to use with respect to our area of the region is equal to the integral from C to D. That's our first function to our second function. Let me clean that up a little bit. That should be a 2. There we go. And that's f of xy with respect to x, with respect to y. Okay, so once again, with respect to x, remember that's going to be between your two x values here. All right. So if you are still writing, feel free to press pause. But we are going to go ahead and look at our first double integral example. Okay, so let's say, for example, we wanted to evaluate the double integral of xy over the region of the area. Let's say, so that's over the region R between, say, y is equal to 1/2 x. Let's say y is equal to square root of x. Say x equals 2 and x is equal to 4. Okay, so a little bit of a mixture of boundary points. Okay, so this time we're looking at our type 1 region. Since we have x is equal to 2 and x is equal to 4 as our vertical boundary line. Okay, and if you look at y is equal to 1/2 x and y is equal to square root of x, those are our x functions. So our first x function and our second x function. All right, so we can go ahead and plug those in. Okay, so our integral over the region R, that's going to equal our integral from 2 to 4 and our integral from 1/2 x, I'm just going to write that as x over 2, to square root of x of our function xy with respect to y with respect to x. Okay, so just like before, we are going to start in the middle and integrate our way towards the outside. All right, so first thing you have to do is find our integral with respect to y. Remember that x is considered a constant. So I'm just going to go ahead and start this down here. Okay, so we have our integral from 2 to 4. So since the x is a constant, the integral of y is just y squared over 2. So you have x y squared over 2. And that's from y is equal to x over 2 to square root of x. X over 2 to y equals square root of x. Okay, you don't have to put the y equals if you don't want to, but it's it can be helpful. Okay, and then that's with respect to x. Because remember, this integral and this dx, we're not even using those right now. Okay, we're just focused on what's in here. Okay, so that becomes, remember, replacing y with square root of x first. So we have the integral from 2 to 4. So we have x times square root of x squared over 2 minus x times x over 2 squared over 2. Okay. And again, that's with respect to x. Okay, so if we keep on going here, we have square root of x squared. That's just x, so x times x is x squared. So the integral from 2 to 4, you have x squared over 2 minus, you have x squared over 4. So you have x cubed, bring that 4 down, it's over 8. So it's x to the third over 8. And you can integrate that with our respect to x. Okay, so if we integrate each one of these, we have x to the third over 3. Multiply that by 1/2. You get x to the third over 6. Minus, you have x to the third over 8. That's x to the fourth over 4. Multiply that by 1 over 8. You have x to the fourth over 32. And that is from 2 to 4. Okay. So we go ahead and plug in our 4. 4 to the third power is 64. So you have 64 over 6 minus 256 over 32. Minus, you have 2 to the third power, which is 8. So 8 over 6 minus 2 to the fourth power is 16. You have 16 over 32. Okay, so once you combine and start simplifying and everything else, you end up with 11 over 6 as your answer. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. All right, so for this example, we are going to evaluate the double integral of 2x minus y squared with respect to the area over the triangle region that we will, of course, call R, enclosed between the lines say y equals negative x plus 1, y equals x plus 1, and y equals 3. Okay, so honestly, looking at this does not tell you much as far as your region. In a case like this, it's best to draw your triangle out so you can visualize exactly what you have. Because once you're visualizing it, you can see exactly where your x and y's and everything else would go. Okay, so in this case, drawing the region will help you visualize. All right. Okay, so what if we have our region here? And make sure it's big enough. Alright, so we have our x and our y there. So if you draw negative x plus 1, let's say this is our 1. Okay, so negative x plus 1 would look kind of like that. Okay, so this is y equals negative x plus 1. So if we want to draw x plus 1, it would look kind of like that. So our y equals x plus 1. And y equals 3. Remember, that's just a horizontal line going through 3. So if this is our 3, we'll say this is 3 here. Okay, so let's say this is our y equals 3. Okay, so in here, this is what we're trying to find the area over this region. Okay, so this is our region. Okay, so you can see here that y actually goes from 1 to 3. Okay, so you see that y equals 1 to y equals 3. Okay, here originally they only gave us the y equals 3. That's why drawing it out helps a lot, because say, okay, now that I drew this out, I can see it goes between 1 and 3. Okay, so that's our C and our D value there. Okay, and now the only thing is, we're left with our y equals negative x plus 1 to y equals x plus 1, which doesn't help us a lot because remember, we already have our y boundaries here. Okay, we can't have 2 more y boundaries. So what do? You just solve for x, and that'll give you 2 x boundaries. So if you solve for x, that would give you x equals 1 minus y to x equals y minus 1. So we have our first y function, and we have our second y function. Okay, so they won't always give you everything, but they'll give you enough to be able to figure out how to come up with your boundaries. Okay, so now that we have our boundaries, we can go ahead, plug those in. Okay, so our second integral of 2x minus y squared with respect to our area. Okay, we're going to make that from 1 to 3. And again, from 1 minus y to y minus 1. Of 2x minus y squared with respect to x with respect to y. And again, always double check, because if your y values are on the outside, then your respect to y should be on the outside. Alright, so we can go ahead and integrate those with respect to x, because we're going to start from the inside out. So, write down from 1 to 3, because that's just going to follow us, just like our dy will follow us. So we integrate 2x with respect to x. That's x squared over 2. The 2's cancel out, so we're just left with x squared. Minus, you have y squared, that's considered a constant. So that with respect to x, the integral of that is just x. Y squared. And that's from 1 minus y, so x equals 1 minus y to x equals y minus 1. And again, your dy just follows right on down. Alright. So, our integral from 1 to 3, remember that keeps on going until we're ready to use it. Same with this. When we're done, we're going to put that back down there. Okay, so we have y minus 1 squared minus y minus 1 times y squared. Okay, minus, and then we're going to do it for our bottom boundary value, 1 minus y squared minus 1 minus y times y squared. And don't forget your dy at the end. Okay, so if we go ahead and FOIL these out and everything else and distribute and all of that good stuff, we end up with the integral from 1 to 3. You have 1 minus 2y plus 2y squared minus y to the third minus 1 minus 2y plus y to the third respect to y. Okay, and once we're done canceling everything out, we end up with the integral from 1 to 3 of 2y squared minus 2y cubed with respect to y. All right. Okay, so we can integrate both of those terms with respect to y. We end up with 2y to the third over 3 minus y to the fourth over 4, but the 2 cancels out here, so that becomes over 2. Okay, and that is from y equals 1 to 3. Okay, so that's going to equal, once you plug in your 3, you're going to have 54 over 3 minus 81 over 2 minus, now plugging in your 1, you have 2/3 minus 1/2, which will give you negative 68 over 3. Once you're done combining and simplifying and getting all the common denominators and everything else. All right. Okay, so if you are still writing, once again, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so what if we wanted to evaluate the integral from negative a to a, the integral from negative square root of a squared minus x squared to positive square root of a squared minus x squared of x plus y with respect to y with respect to x. All right, so I'm just going to go ahead and rewrite our problem. So you have negative square root a squared minus x squared to positive a squared minus x squared, x plus y with respect to y with respect to x. Okay, so starting right here in the middle, you can see that this pretty much looks like from a to b, your first x function to your second x function. Respect to y, then respect to x. So it pretty much looks like this one. Okay, so know we're integrating here with respect to y. Okay, so that gives us the integral from negative a to a. Integrate x with respect to y is just xy. plus integral of y with respect to y is y squared over 2. And that is from negative square root of a squared minus x squared to square root of a squared minus x squared. And that is respect to x. Okay, which means we're going to go ahead and just plug both of those in with our y values. So the integral from negative a to a, you have x times square root of a squared minus x squared plus square root of a squared minus x squared squared would actually just get rid of the square root. So it's a squared minus x squared over 2 minus, you have negative square root of a squared minus x squared. So that's x. Oh, actually, you can put the minus right in front of there. So minus x square root a squared minus x squared plus, again, that just becomes positive since it's a negative squared. So you have a squared minus x squared over 2 and all of that is with respect to x. Don't forget that. Follows you all the way down till you use it. All right. So from there, we can see here that once we distribute this negative, this is positive, this one becomes negative, so those two actually cancel each other out. This will become positive, so it would just be x square root of a squared minus x squared plus x square root of a squared minus x squared will just be the integral from negative a to a of 2x square root of a squared minus x squared with respect to x. No, I don't really need the brackets, but too late, they're already there. Okay, so if we integrate this with respect to x, we go ahead and use u substitution. U is equal to a squared minus x squared. Then our du is going to equal negative 2x dx. Okay, so if we go right down on the side, just showing the work here so we don't fill up the page there. So that gives us the integral. We have our 2 here, so to make that a negative 2, we just multiply negative out here. So we have here our negative, put it right next to each other to make sure it's in the right format. So a squared minus x squared times negative 2x dx. Remember here we didn't change anything, we just added a negative here to counter the negative here. Okay, so really this is just the negative integral of u to the 1/2 power instead of our square root. So u to the 1/2, and this is our du. Okay, so that will just give us u to the 3/2 power over 2/3. So I'll just finish writing that over here. So we have negative 2/3 a squared minus x squared to the 3/2 power. And remember, that's from negative a to a. All right. So if we plug in a, we have a squared minus a squared, which is 0. minus, we plug in negative a, that's a squared minus, that becomes positive a squared, which is 0, which is equal to 0. Okay. Don't you just hate it when you do all of that work and your final answer is 0 or 1? But that's what we did. We did all of that work to end up with a final answer of 0. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. All right, so let's say, for example, if we wanted to find the volume. Let's say find the volume under the surface say z is equal to 1 plus x squared times y squared. And above the region, enclosed by x equals y squared and x equals 4. Okay. Once again, it doesn't look like they gave you enough to get all 4 of your boundaries, but they actually did. Okay, so we know that this is our region. Okay, so we have x equals y squared and x equals 4. Okay, that actually gives us our x boundary. Okay, so that just becomes x is between y squared and 4. Okay, so we're okay there. But we have to figure out our y boundaries. Okay, so the only thing we have with a y in it is this. We can't use our function here because that's not in the region. We have to find the boundaries in the region. Okay, so we use that. Okay, so let me kind of mark that since we already have it. But what if we know that x is equal to y squared and x is equal to 4? What does that tell us? That y squared is equal to 4. What does that also tell us? Well, it tells us that y is equal to positive or negative 2, which gives us our boundary points. Okay, which is between negative 2 and 2. Okay, so you have to be able to kind of look at it and figure out your boundaries. Okay, they won't always give them to you, but they will give you just enough to be able to figure it out. Okay, so now that we have our boundaries, we go ahead and plug it in because our volume, which is the double integral respect to our area of the region, okay, that's going to be equal to the integral from negative 2 to 2 and the integral from y squared to 4 of our 1 plus x squared y squared dx dy. All right, so we're going to go ahead and finish that down here because we're just going to start in the middle like always, and we're going to integrate this with respect to x. Okay, so this one just follows us right on down, so from negative 2 to 2. Okay, so the integral of 1 with respect to x is just x, plus the integral of x squared y squared with respect to x. Remember, the y squared is considered a constant. So you have x to the third over 3. So you have x to the third y squared over 3. Remember, that's from x equals y squared to x equals 4. And don't forget your dy. Okay, so if we go ahead and plug those in, remember our integral from -2 to 2, just like that, our dy follows also when we're done. Okay, so if we plug in our 4, we have 4 plus, we plug in x equals 4, 4 to the third power is 64, so we have 64y squared over 3, or 1/3 64y squared. Okay, minus, now we plug in our y squared with x, that gives us y squared, plus, plug in y squared here, you end up with y squared to the third power, which is y to the 6th power, times y squared is y to the 8th power, over 3. And don't forget your dy. Okay, so if we go ahead and combine those two y squared terms, we can simplify this from -2 to 2, degree 4 plus 61 over 3 y squared minus 1/3 y to the 8th. Or y to the 8th over 3, doesn't matter. Okay, so now we integrate all three terms with respect to y. Okay, so 4 integrated with respect to y is just 4y, plus y squared is y to the third over 3. You multiply that by that denominator, you get 61 over 9 y to the third, minus, this is y to the 9th over 9, multiply that 9 by the 3, so you get 1 over 27 y to the 9th power. And that's from -2 to 2. Okay, so we go ahead and plug in our 2's. 4 times 2, we end up with 8 plus 2 times 2 times 2, that's 8. So 8 times 61 is 488 over 9, minus, we have 2 to the 9th power, which is 512, so we have 512 over 27, minus, now we plug in our -2, we have -8, minus, plugging in -2 here, gives us minus, because it ended up being an odd number of, odd exponent, so that gives us a negative there. So you have minus 488 over 9, plus, remember odd exponent, so that's going to change that sign when it's a negative. So we have 512 over 27. Okay, so if we combine all of our terms, we end up with 2,336 over 27, which rounds to about 97.3 if we round to the nearest 10th. Okay, so you have your exact answer here, and you're rounded to the nearest 10th. Okay, now which one is right all depends on exactly what they ask for. Okay, sometimes they will want just the exact answer. In this case, you give them that. If they want it rounded, you give them that. All right. So if you are still writing, feel free to press pause. We're going to go ahead and move on to our next example. Okay, so what if we wanted to, and this is kind of a new trick here, wanted to evaluate the integral let's say the integral from 0 to 8, and again from the cube root of y to 2 of ex to the fourth dx dy by reversing the order of integration. Okay, so the order of integration. Okay, so all that means is that we're going to switch up our dx and our dy, which means we have to switch those up also. Okay, so how do you do that? Well, I'm just going to rewrite this, but add our little variables in there. So this is y equals 0 to y equals 8, because that's on the outside. And this is from x equals cube root of y to x equals 2 of e to the x to the fourth dx dy. Okay, remember we're just going to switch those up. All right. So what do we know here? We know that we can't just switch those up. We know that y is from 0 to 8. And x equals cube root of y to x equals 2. Okay. So how do we switch those up? Well, we noticed a couple of things. That, remember, this is the formula here. We're going to have our x on the outside. So we know that this is going to end up being x equals y, well, y equals x to the third. Okay, which means our dy, if we switch these up, our dy is going to have to be a function of x. Okay, so using this formula, when y is equal to 0, or when x is equal to 0 rather, then we know that y is equal to 0. And when x is equal to 2, we know that y is equal to 8. Okay? So that actually gives us everything we need. Okay? Because we know that, of course, we are going from x equals 0 to x equals 2. And we're going from y equals 0, but we're not going to y equals 8. We're going to y equals x cubed. Okay, so whenever you have a variable function, you can't just switch that to a numerical value. That variable function follows right along. All right, and that is ex to the fourth dy dx. Okay, so we know our integral from 0 to 2, and if we integrate our function with respect to y, this is really considered a constant, so that just becomes y times ex to the fourth. So y ex to the fourth power, and that's from y equals 0 to y equals x to the third. We know that's dx. Okay, so here we plug in x to the third, you get x to the third times ex to the fourth. You plug in 0, that's just 0. So that just becomes the integral from 0 to 2, x to the third e x to the fourth with respect to x. Now we go ahead and integrate that. Okay, so to do that, we use our u substitution. U equals x to the fourth, and du equals 4 x to the third dx. Okay, so that means we're going to have to multiply this by 1/3. The integral from 0 to 2. And we have ex to the fourth. We're going to move that over here, but we're going to multiply it by 3. If you remember, your 3 and your 1/3 will cancel out, so you have 3x to the third. Oh, not, it should be 4. I'm thinking of my x to the third, and that should have been 4. 4x to the third. There we go. dx. Okay, so you have your e to the u du. Okay, and the integral of e to the u du is, of course, just e to the u. So you have 1/4. We don't need our plus c since it's a definite integral. Okay, so we have our 1/4 e to the x to the fourth from 0 to 2. Okay, so we plug in our 2. We end up with 1/4 times e to the 16th. 2 to the 4th power is just 16, minus, plug in our 0, e to the 0 power is 1. So our 1 is there. All right. Okay, so hopefully these examples help and this video made sense, and I will see you on the next video.